Hi dear students, in this session we are going to discuss a very important conceptual problem in electrostatics, example number 1.8. First I will read the problem. So we have a inclined plane on which there is a mass, there is a block of mass m which is positively charged, is kept on the inclined surface. An electric field E vector is applied parallel to the inclined surface. So what we have to find out in this problem is the magnitude of electric field when the block is at rest. So this is the problem, this is the situation. See the diagram. So we have a inclined plane of length L and the angle of inclination is theta. The height of the inclined plane is h. We have the mass, we have the block of mass m which is positively charged, it has positive charge and it is kept on the inclined surface, and we apply electric field E vector which is parallel to the inclined surface. But what is happening there? The block is not sliding down. Normally when you have a block of mass m, so definitely this will incline downwards. And another thing is the surface is frictionless and also well insulated. So there is no problem in the insulation, well insulated, frictionless surface. So we don't consider the friction. So all these things are very important. So what is the magnitude of the electric field applied here? And the very important point you have to note, the block is at a rest. Block வந்து ரெஸ்ட்ல இருக்கு அப்படிங்கிற கான்செப்டை நீங்க மைண்ட்ல வச்சுக்கணும். Let us try to find out the free body diagram for this. The block is represented as a point here of mass m. This is the block. How many forces are acting in this mass? One is the force due to gravity, that is mg. It is downward force, w vector. And this surface, inclined surface, always offer a normal force which is perpendicular to the surface, that is called a n vector or magnitude n. These things already you have seen in the 11th standard, right? Okay. And another force is there which is due to the electric field because we have the charge q in mass m. So mass m la charge irukku. Appo definitely it will experience a force and that force is represented as QE vector, or simply you can represent as QE, no issue. And all the forces are unbalanced forces. To discuss the problem, to resolve the problem, we need to compensate all the forces. Therefore we have to resolve this into components. That is very important. Already you are familiar with this. That's why I directly draw the components diagram here. So this is the block. So therefore mg is the downward force. Normal will act perpendicular to the surface and there is a frictional force F is equal to EQ or F vector equal to QE vector. All the forces, as you are seeing the free body diagram, this is FBD, free body diagram. So you are seeing the same situation here, and now I am going to resolve this. So already you know that this is theta means, and this also theta, already we have proved this in 11th standard, you refer there. And here this component of the mg is, horizontal component is mg cos theta and the vertical component is mg sin theta. Okay, this is the only components we have, horizontal and vertical components, and in fact the diagrams components will be the same thing. Okay, this one is mg cos theta which is horizontal and mg sin theta is vertical for mg. So what happens, this normal compensate this mg cos theta. Mg cos theta is compensated by normal force and mg sin theta is balanced by mg sin theta is balanced by the force due to electric field. And don't worry about mg. So these are the vectors we have. But what is the point given in the problem? In the problem what we have the block is at rest. So acceleration of the body is 0 here. So the net force acting on the body is 0. That is a very important point we have to keep in mind. Okay. So there is no vertical motion, there is no horizontal motion. So we don't bother about the vertical motion because there is no electric field along the vertical direction. We have electric field only on the horizontal surface, I mean the inclined surface. So we will talk about only this component, sin theta component only we are going to discuss, because the electric field is acting only along the inclined surface. That's why we don't consider this one. We don't consider this one because there is no vertical motion. We consider only this one. We consider only this one. So you take appropriate coordinate system. This is x-axis, this is y-axis, right? So for this we have a frame of reference, and here we have positive x-axis, the unit vector is I cap, and here we have negative means minus I cap, and this is j cap, so no need for this. Now you write down the net force equation. What is the net force equation? Here mg sin theta is along the positive x-axis, so you will get mg sin theta I cap, then plus, then another force is acting upwards, that is QE. It is in the negative x-axis, so minus I cap. There is no acceleration, the body is at rest, therefore the right hand side will be 0. So mg sin theta into I cap is equal to, this minus will become plus, so QE I cap. If you take modulus on both sides, you will get mg sin theta is equal to QE. Therefore the magnitude of the electric field is equal to mg sin theta, right, divided by Q. This is the important result we are getting from the problem. So the solution is, the electric field applied in this system where the system is kept at equilibrium, it is at rest. So the magnitude of the electric field is simply mg sin theta divided by charge. So what are the things are constant here? Sin theta is constant because theta is angle of inclination. We are not changing the inclined plane, so we fix theta constant, and acceleration due to gravity g is also constant. So what are the things can change? So E directly proportional to mass and E inversely proportional to charges. These are the changes can take place. Am I right? So when will we need more electric field? Suppose when mass increases, the electric field, the magnitude of the electric field should be increased sufficiently to keep the block at rest. So in this situation, this is the constant. Suppose if you are increasing the value of mass, you need to increase the electric field so as to keep the mass constant, to rest, okay, to be at rest. And what about the charge? Suppose if you increase the charge, it is inversely proportional to the electric field, so no need to increase the electric field. So you have to decrease the electric field sufficiently. So weak electric field is enough to keep the body at rest. In the case of mass, when mass is increased, we need strong electric field to keep the block at rest. These are the very, very important result we infer here. So one is, as far as mass is concerned, when mass increase, strong electric field is to be applied to keep the block at rest. In the case of charge, when charge is increased, we need very, very weak field. Weak field is enough, weak field is sufficient to keep the block at a rest. These are the very important things. And this electric field can also be represented in terms of the dimensions of the inclined plane, because we know that sin theta is equal to opposite side by hypotenuse. Opposite side h, hypotenuse is length of the inclined plane, that is L, already I have mentioned there. So h divided by L, opposite side divided by hypotenuse. Hypotenuse is L, that is the length of the inclined plane. So h divided by L. So this is the sin theta. So you put there. So E is equal to m into g into h divided by L. M into, because sin theta is equal to h by L. So mg h by L into charge, mg h divided by QL. So there is no change. M and Q as usual, M is direct proportion, Q is inverse proportion. So in the place of sin theta we have substituted H divided by L, that's it. So this is the another representation for this problem. So a very important problem and very important concepts we understand here. In this case of electrostatics, very important problems. You just go through it, you will definitely understand. I will meet you in the next video. Thank you.